Okay, quite annoyingly, I recorded the last video and forgot to put the microphone off mute. So I'll record it again. Okay, so as we were last time, we have two sprites, redrawing the backgrounds, all nice, except if I show, there was a slight problem. So if I take the second sprite, put it over the top of the first, but make it go a little bit quicker. You'll see they aren't exactly clearing the background. What's actually happening there is we're drawing the first sprite and grabbing the background underneath, which is just the maze. We're drawing the second sprite, and when it's over the top of the first, the background we grab for that contains part of the first sprite. At the moment, we're then redrawing the backgrounds in sprite 1, sprite 2 order, so we redraw the background behind sprite 1, which is the maze, and then we redraw the background behind sprite 2, which contains part of sprite 1, which is why we see this little sort of almost see the sprite as it's going over it, it leaves part of it behind. We actually need to draw them in reverse order. So what we're going to do here is let's move this and put reset the background buffer. I'm not going to bother passing in this. It doesn't really make sense to bother passing that in, so we will just store that in there each time. So yeah, so what we want to do is we want to redraw them in reverse order that we grab the buffers. So for now, we don't want to grab there. We just want to get the address, store all the data, and then at the end here, we're now going to store the finishing position, and we're going to do everything backwards, literally backwards, not just doing the sprites backwards. We're going to redraw them from, rather than draw, normally when you draw a sprite, you go from left to right, from top to bottom. We're going to go from right to left, from bottom to top. You don't need to do it that way. You can do it a normal sprite draw as long as you draw the sprites in reverse, but this is, as you'll see, it's just a little bit easier. So we're going to take DE, store the address at the end of the buffer this time rather than at the start, like that. And then when we come up here, one thing to note here is we're doing an increase HL, so we don't have to worry about anything at the start, but that means HL is now off the beginning of the buffer. So when we get here, the first thing we want to do is decrease HL, sorry, to get us to the start of the actual data. I found out that at is the local label loop, so we'll use that. That means all these labels will be relative to this one. So because things like Y loop and X loop get used quite a lot, so you tend to make them relative to the local to the function name. We now need to see, is there any, before we used this to check if there was any data left. Now we're going to have to do a little bit of cheating. Not cheating, just a little bit of maths. So I'm going to subtract DE from HL. Right, so what this now does is we store HL because we're going to need it. We subtract the background start address from it. Obviously we have to do XOR A or something just to clear the carry flag. We could do AND A if you didn't want to. AND A is probably safer if you don't want to clear the value of A. I tend to use XOR A if I know I don't need to worry about A. Don't know my personal preference. So then we subtract it, and what that means is if the current value of HL is above background store, above or equal to background store, carry won't be set. As soon as it goes below, carry gets set, and then we can return. We pop HL there before we do the rec because it doesn't alter the flags, and obviously we need to leave the stack in the same state. So then what we need to do is read that address. Obviously we're going backwards through our data, so we decrease HL. Now, in the sprite drawer, as you see, we draw all graphics and then we step to the next line. So on the very last line, we're going to draw those graphics, step onto the start of the next line, and then store the address. So the first thing we need to do, since we're doing reverse order, is step backwards. And then rather than doing LDI, we'll do LDD. And then once we've done that, we'll go back and see if there's any more to do. So that should... Oh, I've still got a problem. No, if you look... Oh well. If you look at the... I'll run it again. If you look at the the right-hand side of the map, as the faster sprite moves over, it will give you a clue as to what's going wrong. We're offsetting the map. What we're doing is we're redrawing it offset. The reason for that is because we're using LDD and LDI, well, not LDD instead of LDI. This will move the data from HL to DE and then decrease both. But here, when we're drawing it, we draw that last byte, we increase DE because of when we're looping. So the very last DE after the very last pixel at this point here will be pointing to the byte just after the last byte drawn, and then step down to the next row, which will be the first byte that we're going to draw again. We need to actually effectively decrease DE here. Not actually there, but we need to get DE to be 1 byte previous. If we do it here, we're going to actually, because we could just put that at 7, but then it's going to offset too much. What we actually just want to do is decrease D here before we store it to take it back 1 pixel. That means each row will be stepping every time we subtract this. Where is it? Here. Every time we subtract to go back to a row, what we'll be doing is going back to the last actual byte of data, and then we can use our LDD. And there we go. So now as we're drawing them, we're redrawing them in the same order. So that's all good. Good. What I'm going to do now, like I do with the tile maps, I'm going to create a file now. Sprite handler. This is 105. And go to Pac-Sam. We've got many. There we go. Let's take those two sprite functions just to keep everything tidy. And we'll put them into a file of their own. And then down here, we will hopefully still have exactly the same. Okay, so what I've done is I've just tidied it up. I've just taken the sprite function to the sprite class, sprite file. Right. What we now need to start looking at is double buffering, because they flicker, it's horrible, and as we draw more, it becomes more of a problem. And also, one of the other problems we've got is obviously we're just using a delay loop here, which isn't very nice. So I'm going to initialize function. Don't think we do a DI. Oh, we do a DI at the moment. Don't actually need to. We could take all of this. No, we're just going to set up the interrupts in here. There's lots of information on interrupts. I know some people say you don't need to set up a 257 byte table. I tend to. And I'm going to set this table up at... there's lots of address. We're in the top half. of memory. So let's stick our table at, we need 257 bytes plus the space to put the interrupt handler. So if we put the interrupt handler FE, FE, we can't put FF because then we're enough space. So if we put FE, FE, is the data, this is the address. And we're going to want to put that into FD. FD00 LD BC, 100 26. That will obviously take write A, which FE into FD. We'll then copy from HL to DE, and we'll do that 256 times. So the last one we'll do will be into the 257th byte. So that will set up our table. And now all we need to do is load I with A. Before we can enable interrupts, we need to have an interrupt routine. It's not really vertical blank interrupt because obviously you can have more than one, so let's just call it the IM2 handler. For now, I'm just going to do EI and rect. We're just going to look at this because I'm fairly sure so yeah, shown from interrupt, enable the interrupts because they'll start disabled. We're not going to do anything else, but what we need to do is sorry, FE. So FE, we need to put in jump, which is back up here. The opcode, as you can see, is C3. Let's use that instead. Increase HL. Put the address. Okay. Okay, so we now got an interrupt handler. So after we've done that, we go good. Doesn't matter now that we enable the interrupts at the end of that, and we're paging out RAM because obviously we're not calling anything, not the interrupt handler. So hopefully, if I've got all that right, which I haven't, we've now got a problem. That'll be when the interrupt kicks in. Just run that again. Oh, forgot one important thing here. Forgot to tell it we're in IM2. Oh, didn't compile it. Knows we're in IM2. What did we do wrong? Let's just check we have set up a table. Oh. Obviously the iReg is meant to hold the start of the table, not the start of the interrupt routine. Okay. Sometimes get the feeling things aren't going to go well today. Let's just go and check. So, yep. Helps if you write the routine at the right address. Let's go to, so we're putting lots of AFEs, so the interrupt should be here, and 9080 should be our interrupt handler, which it is not. I got these the wrong way around, probably. There we go. Close that one down. Forgot which way you put the slashes, so that's getting a low byte, and that's getting a high byte. Okay, so it's now, we're not doing much with this interrupt handler, but we have an interrupt handler running, so we can now back up here where we've got our loop. I want to keep loop. What we can do is stick in halt. That just waits for the next interrupt. Also, a bit fast now because it's actually running on the V blanks. They're not flickering because we're probably drawing them well within the vertical blanking period. Could probably. No, it doesn't really matter. But yeah, so we've got an interrupt handler running. You can use halt. There's nothing wrong with using halt. I tend to use a flag, so I can use it for other things, but we'll stick with halt for now. So here will be one of the other reasons is if I want to use a line interrupt or anything, we can't use halt because that could trigger when the line interrupt happens. Because say halt just waits for the next interrupt. So now we've got an interrupt routine working. The next thing we're going to look at this time is our double buffering. So I've got this variable view page. So we've got a render page and view page. Sorry, that was a slip of coffee. The point of double buffering is we are showing the user one screen while we're building up the screen that they're not looking at, because then we can take as long as we want. Take half an hour, doesn't matter. They're not seeing us do anything, they're just seeing the screen that we've done. Once we're finished drawing the screen, we wait for a vertical blank and then flip these two over, so then they're seeing the one that we've just drawn, and we can then work on the screen again, the other screen that they're not looking at. So effectively we've got two screens and we keep flipping between them. So what we'll do here is we'll call a function called flip buffers. Slipping to my C++ there, putting a semicolon at the end. So swap over the buffers. View buffer. LD B, A, LD A, render buffer. That's what we called them. Yeah, view and render. And now we can LD view buffer with that. So now view buffer goes into B, take the render buffer, overwrite view buffer, and flip back. Good. Right, so now we've got that. If we go up to our... I'm not actually changing the page at the moment. This is where we change the pages. So we could put this in. We may move it out again at a later date, but so we take our render page, set that into lower memory, and now we will take our view page, as that's the one we're looking at. I've called it buffer. View page, view page, view page. Helps you use the right names. Okay. Well, that's all going horribly wrong, isn't it? As expected. You'll also notice the tile map wasn't drawn, because to begin with, we haven't got anything set in lower memory, so we could just do a flip buffers to start with. What that'll do is just set the correct page to render. And you'll notice it's going very horribly wrong, as expected. If you think about it, what we're only doing is we're only drawing the map onto one of the buffers. So what we could do is do it twice. So we got a render buffer, or we're looking at one buffer, we draw the map, look at the next buffer, draw the map, before we do anything. And that will stop the background flickering, because the same screen is the same buffers on both. But as you can tell, our array sprites has now gone very horribly wrong. And it's expected. We're looking at buffer, let's call them buffer 1 and 2. We're looking at buffer 1, we draw the sprites, we're grabbing the backgrounds. We then flip to buffer 2, and we call array sprites, which has currently got all the information we've stored for buffer 1. So any sprites that have moved between the periods have all going horribly wrong. What we need to do is remember the buffers on each page. Okay. There are two ways doing this. We could create. That will do a. We can do this, and we can go. So we can have create two separate buffers, and then when we flip buffers, we want to flip between them. So the trouble is that's quite complicated. I was going to just do it quickly, but it's actually quite complicated because we'd have to go and then store this as a variable somewhere. I suppose we could. Then we have to read it. No, we'll go straight for the easy option. The easy option comes down to the fact that when we flip buffers, we flip two 16K pages at once, sections AB or sections CD. In this case, we're flipping AB. The screen takes up 24K, which means we've got a nice little 8K sitting at the top of the screen. So the cheat here is this background store if we let's take both of those. Let's try and think of the best way of doing it. Call these screen variables. And we'll store these at buffer 15. offset 4 and org4 because that's what we're doing. Now these are variables that if I now compile this, hopefully it'll still compile. But if we look at the map file, hopefully what we'll see is look for it's still let's just delete those again. It's because I forgot that I hadn't gone back to Pac-Sam. So if we compile this, look at our map file, what we'll hopefully see, we look for background store. It wasn't 4000. Yeah, it's put the background store address 4000. We don't even really need to do the dump at all, because these can just be define space 2 because we want space 2. It sometimes gets confusing, so I tend to put the dump anyway. Right, so put this at 6. Putting that in just means we're not accidentally overwriting and using up space we don't need to. So it's 6000 because we want 0 to 6. That's the size of the initial screen. 2 here because we're onto page 15. I've picked page 15. We could pick page 13 because that'd be that page. We only need to actually set up 1. You might be thinking, why? We've got 2 screens. It doesn't matter because when the addresses of these variables is all we're worried about here. Oh, just done it again. Really must look at changing this plugin. So yeah, so if we compile that, oops, wrong button. There we go. So if I compile that, we look at pacsam.map. This is at 6000, and then we've got 6002. Oh no, I can't put them in there unless we put the variables to the end, because you'll see it's changing all these addresses and compiling all these. Which isn't what I want to do. So let's create a new file. And call this screen variables. Yes. So now I'll grab all those for now. Go to screen variables, paste them in there. I'm actually going to take that out of there. And in Pac-Sam at the bottom, we'll move it and call those screen variables, and all we need to do is come in here and get rid of them from here. The reason is you can see quite easily that you've changed the address, because otherwise you put an include in the wrong order. Like there, data came after variables, so it moved all the data. What I'm also going to do, just because I tend to, so here I'll call screen SCR buffer 1 EQ 14 SCR buffer 2 EQ 12. Okay, just so we can move them if we ever want to. EQ just basically sets that to that value so we can use it in other places. Okay, so if we now look at the map file, that's better. So you can see what we've now got is background store address and background store at 6000, 6002. All the rest of our data is in sprites are in the actual top end of memory. Now you might wonder why I haven't created 2 of these. The reason being is when we flip buffers, we obviously change the physical page in lower memory. So we're looking at page 1, and we're grabbing all the backgrounds for page 1 and have our variable, and we're storing all that into the top half of that screen buffer. When we flip buffers, we bring in another page. All that information is then disappears, and we're ready to when we do screen 2. The good thing with this is it means every time we bring in a screen, we also bring in all of the data for the restoring of the sprites that were on that screen, because they're stored within that screen's memory pages. So we don't have to do any buffers, we don't have to do anything clever. We flip buffers, presto. The only thing we have to do is set up the screens. We need to set those, because obviously at the moment we're not setting. Actually, we don't need to do this. We don't reset the background address at the very start. Again, I could do that the same way I've got here. And so we draw buffer 1 and clear its thing, and we flip the buffers to bring in our next page and clear the buffers. It's a little strange to think about, but as I say, if you imagine those two 16K pages, we've got the 24K of the actual screen, and then we've got this extra 8K which stores all the information we've pulled off the screen. Comes a little bit more tricky if you need more than 8K, but I can't imagine we will. We store all that data for those sprites that we've grabbed in there. So when we bring in the next page, that's all safe. And now all we're interested in is restoring. When we flip buffers again, page 1 comes back with all that data that we stored to clear the sprites that were drawn on that page. It just means we're cheating a bit. We're getting the double buffering to handle storing the sprites data and making sure that we're restoring the sprites in the right places for that screen. So there we go. We've now got this nice little sprites, double buffering, quite happily. I say if we turn off the tile rendering for one of these buffers again, we'll have the flickering backgrounds, but as you'll see, we're not getting that issue where we're replacing bits of background that we don't need to. So that works quite well. What else can we do? Let's stop our sprite mode. Let's go down to one sprite again for now. Let's not. Yeah, we'll keep them moving for now. Get rid of this sprite here. Okay, so let's go down to one sprite. What we can do in our sprite handler is bracket, because we might say it's running too quick. So you could actually decrease our VB counter. Go into the variables. And then, as I say, one of the reasons we can do this is because if we start putting in line interrupts and other sort of interrupts, we know we're waiting for the vertical blanking interrupt. So yeah, so LDA. Now all we do is sit here and we read the VB counter. And while it's not 1 or not 0, we can go back to our loop. Ooh. Not expect. Oh. Important thing of interrupt routines. Always make sure you leave the stack in how it was. Oh, well, that should have worked. One of the VB counter, read a VB counter out. That is puzzling. That's very puzzling. Let's stick a breakpoint and restart. Probably done something very stupid. Okay. So that's currently waiting. Let's go and put a breakpoint in our interrupt routine. Decrease it to 0. Sorry, phone. Let's see where we are. We've got more than one interrupt hitting quite quickly. Did seem to have. I've forgotten quite well, so let's run it again. Okay. No, breakpoint in there. Okay, so I'm just going to go and put my breakpoints in. Okay, so with 1, we're on to 0. Go straight back into the same interrupt handler. I feel it's something very obvious that I'm missing here. As to why we go back into the same interrupt handler. It's going to be if I flick. It's going to be to do with one of the. I'm sure it's going to do one of the other interrupts kicking in. So let's just set the interrupt routine right. So in a comma 249 and if it's when it's low, so if it's 0, so it's not 0. Well, try if it's 0 to VB interrupt, which is this one. And then okay, let's see how that works. There we go. Yeah, it was just an additional interrupt kicking him. The speed looks a bit better actually, more what I was expecting. So, as you see, what we're doing now is we read the status register, check if it's a vertical blanking interrupt. If it is, we go and do our VB counter. What the advantage is, say we can just set 1 and use it as the vertical blank happens. If we decide the game is running too quick and we just want to slow everything down, you could stick this at 3, and the entire game's running slower. Generally, you don't want to. 1's usually what you aim for. Not all games run 1. Some games will run at 2. And actually, technically, that's wrong. Because you would normally set this here once you finish, because then it's waiting for. You're doing everything. So if you took 3 frames, let's do that. In fact, let's do reset VB counter. We need to put all this to. We'll put some better setup code and tidying up code at some point, but for now we'll just clear the VB counter. We can get rid of that. We can go back to that. One thing we do want to do is, obviously, if we're doing it this way and we currently take 2 frames, we're going to set VB counter to 1. The drawing takes 2 frames, so it's going to go down to 0. By the time we get back up here, it's going to be at -1, 255. We're going to sit there for ages. So down in our interrupt routine, we will want to. Again, there's always different ways of doing it. Let's just do it the easy way. JPL JR 0 BB return. Okay, because we know we're always taking. If I put probably about that many in, it's going to be more than the frame. Maybe it's not. One thing you can always do to tell. This is a classic way we used to be able to work out timings. You can count them, but why bother? And we can, because you can have multiple colours, so we can. It's now out of range. That's probably why I didn't do it before. I didn't notice. Yeah. Oh, we're completely blowing the. Look at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So it's 30. So we're currently rendering 6 times 12. 6 times 12 times 30. Oh no, this is not overblowing the. Thought it might be overrunning the background. Oh, I know why it's going horribly wrong there. Let's take this down. Terrible when you're fixing up issues with. Just test code to check things. Obviously, we weren't resetting the information every time. So let's just. I know it's horrible, but it'll. Trying to show you some things we use. So there you go. So we're still running. It's taking about half a frame to render 5 of those. So if we do 12, it's certainly taking more than a frame. If we draw 30, it will certainly be taking more than a frame. So it's slowed down, but as you can see, as soon as it gets down and clears the background, we see the black flicking around, we're instantly going, oh, we don't need to wait. Whereas if I increase this to, let's reset this to 10. Oh, sorry. Counter. So we say we're going to wait 10 frames. There you go. You can see. Obviously, it flashes because for 9 frames or so, or for however many frames it is that it takes to draw, it's going to be one colour, and then for the rest of up to 10 frames, it's then all going to be black. But it's quite useful to be able to visualize how long things take. Anyway, so that's the double buffering and fixing up the sprite redraw. What we can do is look at a very quick start the sprite animations. So let's create a new file. Animation tables. We'll call this pack left anim. Okay. So at the moment we're only using 1 frame, but as we said, we have closed, left 1, left 2. So it's going to go closed, left 1, left 2, left 1, closed. We could do, let's start with a very basic example of how we could do that. Left 1, left 2, left 1, closed. So there we go, we've got a nice little animation. What we'd probably need at the start is number of frames. So compared to this part, we'll put this part of Pac-Sam, we'll move it again later. So at the moment, rather than what we're doing here, this is the animation. We actually need a sprite structure really now, which we will look at probably next time. For now, we're just going to do a basic sprite animation. So that's the animation we want to play. In our variables, just realised to call it Pac-Mac. It's better. So we'll call it Pac-Man frame. offset. So now, rather than this, we're going to read Pac-Man frame. But we need to work out which frame. So we get the offset. We get our random offset. Now, if we move that to E, is probably easiest. The reason we need to add it twice, I mean, we could actually do it that way. It's probably a bit quicker, even though we're using more instructions. Because each of these two bytes. So we want to know how many frames we've got, get the current offset, get to know frames, and then we can do LD read the animation frame. Store the frame we want to draw. At this point, we've still got the animation offset here, the current one. So we can now say move on to the next frame. So LD, so increase A, compare B, compare 6, compare B. JR if not 0, no reset. Else we want to XOR A because we're just making these simple looping animations. You can make ping pong play once and everything else. We may need some of those at a later date, but it's fine for now. And we store this new anim offset, and presto. That should, what we'll do actually is we'll call this animation update. As you can tell, we'll stick this into its own function at some point, but we will need to just make some tidy up before then. Okay. Should be, oh, because we haven't down here. We can now include the animation tables. I hope we will now see it is something going very wrong. It's quite what I expected. So passing these, just check we're passing in anim left, passing in left anim. Oh, we're probably not resetting any of these variables. Maybe, I don't think that'll be the cause, but so Bloom frame, we increased HL because we pulled that in, so we're now on the first one. So if this was 0, double it's still 0, so not moving on anywhere. Reading in E, increase HL, reading in D. Oh. Seems to have made it even worse. So increase A, compare it B, we're not 0. So no resets, we store this back in frame offset. Well, let's see what's going on. So obviously, looks like when it comes to reset, but well, same problem is whenever you bring in the debugger, you're going to be in the interrupt, but let's say okay. So HL is 8204. We could just double check that's right. It should be. We look at our Pac-Man left somewhere in here. We should have a 8204. Okay. Several of them running. Got full frames. Our offset is -1. That's not to help. Certainly not going to help. Oh, of course. I've spotted the problem. A problem. With doubled A here. Just you grab it, it'll be easier. Close these. As you can see, we're now animating far too fast. It seems to be probably is too fast. So yeah, so this is a basic animation. As we said, it's going far too fast. What we could do is put, so we know there are 4 frames, and we'll say we want to display each frame for 4 frames of animation. We want to display each frame 10 times. So this is one thing we can do. Pull that bit of data out as well. If we get to variables, what we now need to anim delay. Let's go clear this up here. Okay. When we do the animation, do we need to update? No, sorry. Decrease it. So we actually want to set this to 1 is probably the easiest thing. So the first time in, if it's one frame, take each one is displayed 1 frame, comes in, decreases it to 0, and if it's not 0, we've done, but in case 0, right, we're okay, so we now need to update something. So we can read reset the anim delay for whatever it is for this animation, because in between we may have switched animation, so we just reset that, and the rest should stay as is. Now, I see why it looks strange. Let's make it even slower, it'll make it more obvious. let's also stop him moving a second. It's quite distracting. As you can see, I've got my frames the wrong way around. So he goes open, half closed, open, never closed. So it should have been 2, 1, 2, closed. Oh, no. There we go. So open, 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 closed. If we put this back down to say 10. Oops. Keep forgetting. We probably only want it about 4. I'm going to say 6. There we go. And so we can have left, right, B, left, right, up, down, up. Okay. We could just read. Is there an easy way? I was going to put the keyboard reading routine in. I don't. No. I'm going to leave. We're just over the hour, so it's probably enough for one video. But just to show you, with those in now, we can. What I could do is just show all the animations. A little counter called test. Reset that up here. And we will do test decrease LD. So what we're going to do here is, so it's just a horrible test, so test delay, decrease it, and it's not 0. Otherwise, I will reset test delay. I'll call it test frame. Increase test frame, and do it 3 because we've got 3 animations. Put that back in there. This is very horrible because I'm going to just stick some data in the middle here. Oh, I can't even bring myself to do that. So what we'll do here is we'll have test list. It's okay. So then what we'll do here is we'll load A with test frame again, in case we skipped it. Add A, A to double it. Call test list. Add HL, DE, LD, A, cover brackets HL, increase HL, LDH with HL, LDL with A, and we can get rid of that. Okay, very nasty, very, very nasty, but it's relatively quick. Hopefully. So we'll do a second in each animation. There we go. Until next time.